Hello, welcome to your lesson on exponential functions. All these functions shown here are exponential. Notice they are functions where the exponent is the variable. Right? Exponent is a variable, exponent, and exponent. Let's take a closer look. These are a big family of functions important in modeling many real-life phenomena, so very important to understand how these work and how to model them. Let's take some notes. I don't think you have a notes page, but let's note down most important things. So exponential function, first of all, is a function of this form. F of x equals a to the power x. Again, we have a base number and then the variable is the exponent. In this case, a values must be values greater than 0 and a cannot be 1. So let's begin with exponential growth. Both of these functions here are exponential. We can see we have a base value that's greater than 0 and the exponent is the variable. These two are exponential growth functions. We'll see why. First of all, let's figure out what these values are. If x is -2, what is y? Well, when you have this, when you have a negative exponent, you can bring that to the bottom, 1 over 2 squared, which is 1 over 4. Next one, what would that be? That would be 1/2, because -1 there, you can bring it to the denominator, 1/2. Okay, next one, 0, 2 to the 0 power, 1. Anything to the 0 power is 1. And then we have 2, and then we have 4. Try that with y equals 3 to the x power. First one, oh, by the way, sorry, here's the graph of that first one there. If we plotted all those points, we would get that. This is called exponential growth. And we'll talk about some important things about that graph in a moment. Okay, this one, first one is 1/9. Again, if we put -2 here, we can rewrite it as 1 over 3 squared, which is 1 over 9. Next one, 1/3, then 1, 3, and 9. Plotting that graph, now we have both of them together on here. The second one is this purple one. That graph, you can see it has a larger slope here. It's rising quicker, in other words. And that makes sense. When the base is the larger value, the resulting y values will be rising at a quicker rate. Otherwise, the two graphs have many things in common. First of all, what is the domain of both of them? Okay, the domain is -infinity to infinity. If you remember how domain works, domain is all the possible x values that a function can take on. In this case, if you followed both these functions to the left towards -infinity, they would just go forever that way. If you follow them to the right, they're both rising forever, but they're rising diagonally, therefore they will eventually cover all possible x values. So the domain is all possible values, or all real values. How about the range? Well, if you look closely at the graphs, you will notice they both get close to y equals 0 here, but they never cross it, never go below. And that is something that we have there that's called an asymptote. Both graphs will forever get closer to y equals 0, but never get to it exactly. So that means our range is y values from 0 up towards infinity, because they go forever in the positive direction of y. And finally, what's the equation of the asymptote? Well, that's the equation y equals 0. Another key thing about these graphs is that they both pass through the point 0, 1. And the reason is we see that point right here, 0, 1. When you put 0 in the exponent here, you're always going to produce 1. So all these graphs will pass through 0, 1. Okay, so now let's look at exponential decay. These two equations here are exponential decay functions. Let's take this one and rewrite it in this form. What will this one look like if you rewrote it like this? Well, it'll be this. Again, the reason is we have a negative exponent there, so we can write 1 over 2 to the x, and that's the same as this. And this one here, rewrite that one. That would be 3 to negative x. So notice these are just backwards and forwards versions of each other. Those both show exponential decay. They're both exponential functions because the a value is greater than 0. You can see this a, or base value, is greater than 0. Let's see what happens when you fill these tables. Let's put -2 into this one and see what we get. Well, that will work out to 2 squared, which is 4. Next one will be 2, then 1, then 1/2, and then 1/4. So let's see what that graph looks like. What's happening with that graph? Oh, let's fill this one in first. So we have 9, 3, 1, 1/3, and 1/9. Again, if you put -2 in here, it would become 3 squared, which is 9. If you put -1 in there, it would be 3 to the first power 3, and so on and so on. So there's our two graphs. There's the first one, there's the second one. Notice they're going down, 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 down. So this is exponential decay. The domain. Well, as before, the domain is from negative infinity to infinity. They both go from negative all the way to positive x values. And the range, the same as before, right? From 0 to infinity, but it doesn't go below 0. So the equation of asymptote, again, is y equals 0. And again, they pass through the point 0, 1. So very similar to the last ones, but now they're just going this way. Okay, so those are exponential functions. Let's recap through this diagram, right? Here's these 2 to the x, 3 to the x, 4 to the x. It gets steeper as you go. And here's 2 to the negative x, 3 to the negative x, 4 to the negative x. It gets steeper as you get a bigger base value there as well. Okay, and they all pass through that key point. They have an asymptote there at y equals 0. They pass through the point 0, 1. In both cases, we see that point there. Okay, now that you have those on your mind, let's take a look at taking this further. We're going to transform these. So do you remember transformations? Let's say you had a basic quadratic function, which looks like this, a basic parabola, and now you added 2 to it like this. What transformation is that? Well, as you may remember, when you add to the whole function, right, this is like the whole function plus 2, it means you're saying y plus 2, so you're moving it up 2 on the y-axis. So it translated 2 units upwards, or vertical translation. How about this one here? What if you took the whole function and subtracted 3? In this case, you have your basic x squared function and you're subtracting 3, so you're moving down now, down 3 on the y-axis. So it's down here with that point became this point here. Everything moved down 3. How about this one? Now it says x plus 1 in parentheses. It's not the whole function plus 1, it's x plus 1 inserted into the function. So if you remember, this would create this function here. So that x is replaced by x plus 1. So we have x plus 1 squared. And now this is not an effect on the y values, it is an effect on the x values, right? This is affecting y because we're adding it to the entire function. This is affecting x only. And if you remember with the x ones, it does the opposite of what you see. If you see plus 1, the function moves negative 1 on the x-axis. So that is a horizontal translation, 1 unit to the left. How about this one then? Okay, horizontal translation, 2 units to the right. And remember that x minus 2 again replaces that entire thing. So this is just a recap. Hopefully you remember transformations. Let's look at what we take. If we take this whole function now and you make it negative, what happens when you make this negative? What kind of transformation is that? Well, that negative will be applied again to the entire function. We can see it here, negative entire function. So negative that part and that part. Imagine negative multiplying everything. Now, negative to entire function is making all y values negative. And if all y values are made negative, then this part here, those values would then flip over. It's a reflection over the x-axis because all the y values are made negative. Next one, imagine applying this rule to this one. What would happen? Again, reflection over the y-axis because we're making the entire function negative, so all y values are made negative. And there's our new function that all multiplied negative, and it would look like this. And this one now, what would happen here if you did, notice the negative is now affecting the x values, not the y values, it's affecting the x values only. What would happen now? So that function would now flip over the y-axis, because if the x values are made negative, so these x values would now be across here, right? These negative x values would now be positive, because they're made negative. How about this last one here? Again, it's the x values that are affected, so into this function here, that x is replaced with a negative x, so notice that that x turns into a negative x. And again, the effect is that the x values are made negative, so this reflects this way, and it ends up being here, and that is a reflection over the y-axis. So that's a recap of transformations, something we've studied, but just bring your attention back to it, because now we're going to look at transformations for exponential functions. So here's a basic exponential function, base 2 power x, so 2 to the x function right here. And we're going to see what happens when you do this transformation. So here, notice, we're adding 2 to the x. So what effect would that have? Well, that would move the entire function left 2 units because we're affecting x values. We go left on the x-axis 2. Remember, we do the opposite of what we see. Move it like that. And this little thing I have here, because it's sometimes helpful to find that one point to help you draw a better graph. So it's easy to put 0 into any of these functions. So if you put a 0 in here for x, you get 2 to the second power, which is 4. And that allows you to plot that 0, 4 point, which helps you get a better graph. Okay, next, this one here. What effect would that putting that negative in front of the function do or have? Well, that would reflect it over the x-axis, because we're making the entire function negative, so y values become negative. So that function flips over like that. That point, which used to be 0, 1, is now 0 and negative 1. But the asymptote remains the same. Next one, what effect would this have? Well, here we subtracted 3 from the entire function, so it goes down 3 units, right? From the entire function means subtract 3 from the y values, so the whole function goes down 3 units. And whereas the asymptote used to be y equals 0, well, now it's y equals negative 3, because if it's going up and down, that asymptote will go up and down with the graph. So now it's here. Next one, what's happening here? Well, the negative is applied to the x only, so again, it's a reflection over y-axis. Notice that this graph has flipped left-right over the y-axis, so now it's like this. And we already know that's an exponential decay function. Last one here. Well, we have function, and two things happened. Plus 3 to the entire function, so went up 3 units, and negative 1 for the x values, so that means move 1 to the right. So again, just like with this one, the asymptote here moved down, but here the asymptote moves up to y equals 3, and then the entire function moves 1 unit to the right. So that point, which used to be 0, 1, went up 3 and over 1, and it became, what did it become? 1, 4, 1, 4, up 3 over 1. All right, that's the basics of transforming those. Make sure you understand those clearly. Pause here if you need to. Okay, let's do some problems together. Consider this function. We can see it's an exponential function which has been transformed. Find the y-intercept in the equation of the asymptote. Well, with these, it's often easiest to actually begin with step C here. Sketch the graph. All right, so let's sketch the graph. Well, the graph looks like this, right here. The red one is the basic 2 to the x power function, and then the blue one is with this transformation. Again, it moved up 3 units. So that point, which used to be 0, 1, is now 0, 4. And the asymptote, which used to be y equals 0, is now y equals 3. So the blue one is our current graph here. Now, what's the y-intercept? Well, the way to solve the y-intercept, anytime you want the y-intercept, you make the x value 0, right? To get this y-intercept here, x is 0. So you put 0 into the function, put 0 in here, and solve it, and you get 4. So the y-intercept must be 0, 4, and that makes sense. It matches what we have in our graph. And the equation of the asymptote, well, y equals 3. Okay, let's try B. Well, B, the domain and range, the domain of the blue one is all real values, right? It moved up and down, but the domain remains all possible values, negative to positive. And the range, well, now the asymptote is here, so now the range is not from 0 to infinity, the range is from 3 to infinity, or in other words, y values must be greater than 3, right? Y values must be greater than 3. That's our range. Finally, it says using your GDC, solve the equation. So solve this equation on your calculator. This is your graphing calculator, right? So the way to solve that on your calculator is to graph them and find their intersection. Let me show you how to do that. Okay, here I have the calculator. Let's try it out. Well, first you're going to go to y equals to graph it. You're going to put in your two functions. One of them is 2 to the power x arrow over plus 3. And the other function I'm going to enter is y2, 2 plus 3 to the power negative x. Okay, you're going to graph those two. Let's see what it looks like. Oh, I got a stat plot on. All right, let's take a look. So maybe your graphing window wasn't right. So when you went to graph those two equations, which you punched in here, the graph wasn't looking right. So you pressed graph and something wasn't right. Well, the one way to fix that is to press zoom, and number 6 is zoom standard. So I'm pressing that. Zoom standard basically means set this to a standard window, which means plus 10 here, minus 10, plus 10, minus 10, right? So, and within that window, I can see the two graphs. So I can see one, and the second one's going to come in right away. And now I can find the intersection, because by setting this equation equal to this one, it's saying when is that graph equal to that graph? They're equal when they intersect. And to find the intersection, we're going to press second, trace, which is calc, and then intersection is number 5. And then we're going to say it's first curve. It's asking which functions are you looking at. Well, here we only have two graphed functions. So if you look at the cursor, it should be on one of the two functions right now. It is, so I'm going to press enter. And then now it's flashing on the second curve. Enter. Great. Sometimes you'll have more than two curves, so you have to select the two you want to find the intersection of. And then guess means get me close to the intersection you're looking for. So right there, enter. And we have our intersection right here. That answer should match what we have.